Hello, and welcome back, or perhaps for the very first time, to Sleepy Wiki. Find a comfortable space, let your shoulders gently drop, and allow your breath to slowly deepen, easing you into a state of quiet calm. Tonight, as the world outside begins to quiet, we'll turn our gaze inward, not to the vastness of galaxies, but to the equally profound, infinitely intricate world that lies just beyond our everyday perception. We'll explore the microcosm, the universe within the minute, the wonders hidden in the very small, where life dances in forms unseen, and complexity blossoms from simplicity. Imagine ancient whispers telling tales of tiny kingdoms, of invisible architects crafting breathtaking structures, of life's fundamental secrets held within a single drop. It's a journey into the quiet hum of existence at its most fundamental level, a gentle exploration designed to soothe your mind as you drift towards slumber. If these quiet journeys bring you a sense of peace, and if you feel so inclined, a gentle like or a soft subscribe always helps others find their way to our sleepy corners of knowledge. Now, let us begin our quiet descent into the marvelous depths of the microcosm. Imagine, if you will, the quiet hum of the world around you, the rustle of leaves, the distant sigh of the wind, the gentle beat of your own heart. These are sounds we can hear, experiences we can feel. But beneath the surface of what our eyes can behold, beyond the reach of our fingertips, lies an entire universe, vibrant and bustling, yet utterly silent and invisible to our everyday senses. This is the realm we call the microcosm. It's a world that exists within every drop of water, on every speck of dust, inside every breath you take, and indeed, within every cell of your own body. The microcosm is the universe of the infinitesimally small, a boundless expanse populated by beings and structures so tiny, they defy our ordinary understanding of scale. To truly appreciate its grandeur, we must first learn to quiet our minds and open our imaginations to a different kind of vision. Think for a moment about a single grain of sand on a vast beach. It seems small, doesn't it? Almost insignificant. Now, imagine shrinking that grain of sand down, not just a little, but profoundly. Shrink it until it becomes as tiny as the period at the end of a sentence. Even then, we're still not quite there. We need to go much, much smaller. Consider the width of a single strand of your hair. It's incredibly fine, perhaps around 50 to 100 micrometers across. A micrometer, sometimes called a micron, is a unit of measurement that helps us navigate this unseen world. It's 1/1,000,000th of a meter. If we were to line up 1,000 of those hair widths, end to end, we'd only just reach a single meter. Now imagine stepping onto that single strand of hair and looking down. The world below us would open up into a landscape of breathtaking complexity. It is at this scale, the micrometer scale, that we begin to truly encounter the inhabitants of the microcosm. Here, we find the bustling cities of our own bodies, our cells. A typical human cell, like a skin cell or a muscle cell, might be anywhere from 10 to 100 micrometers in diameter. Each one is a miniature world in itself, enclosed by a delicate membrane filled with intricate machinery working in perfect, silent synchronicity. Within these cells, tiny power plants called mitochondria hum with energy production, and vast libraries of genetic information, our DNA, are carefully stored and accessed. They are the fundamental building blocks of all life as we know it, from the smallest blade of grass to the largest whale, and indeed to you and me. But the journey into the small doesn't end there. We can shrink even further past the cellular level into a realm measured in nanometers. A nanometer is 1,000 times smaller than a micrometer, or 1/1000th of a meter. To put that into perspective, if a human cell were the size of a large house, a nanometer-sized object would be like a tiny pebble on its roof. In this incredibly minute landscape, we encounter entities like viruses. These fascinating structures are often just 20 to 400 nanometers in size. They are like exquisite geometric puzzles, often consisting of genetic material, DNA or RNA, encased in a protective protein shell. Are they alive? That's a question scientists still ponder, as viruses can only replicate by hijacking the machinery of living cells. They exist on the very edge of what we define as life, a testament to the diverse and sometimes ambiguous forms existence can take in the microcosm. And then, even smaller, we find the very essence of matter itself, molecules and atoms. Molecules are groups of two or more atoms held together by chemical bonds. A single water molecule, for instance, is made of 2 hydrogen atoms and 1 oxygen atom, and it's only about 0.27 nanometers across. Atoms, the fundamental particles that make up all matter, are even smaller, typically around 0.1 to 0.5 nanometers. Imagine the chair you're sitting on, the air you breathe, the warmth of your blanket. All are constructed from these incredibly tiny dancing particles, constantly vibrating and interacting in ways we can barely fathom. How do we know about this hidden world? How do we peer into these depths? For centuries, this realm remained a mystery until the invention of the microscope. Early light microscopes, using lenses to bend and focus light, allowed pioneering scientists like Anton van Leeuwenhoek in the 17th century to first glimpse animalcules, his term for bacteria and other single-celled organisms, swimming in pond water. It was a revelation, like discovering a new continent teeming with life. Today, our microscopes are far more sophisticated. Light microscopes can magnify objects up to about 1,000 to 2,000 times, revealing the intricate details of cells and larger bacteria. But to truly dive into the nanometer scale, to see viruses, molecules, and the internal architecture of cells in exquisite detail, we rely on electron microscopes. Instead of light, these powerful instruments use beams of electrons, which have much shorter wavelengths, allowing for far greater resolution and magnification, sometimes hundreds of thousands or even millions of times. They paint breathtaking portraits of a world previously unimaginable, showing us the delicate structures of a virus or the intricate surface of a bacterium. This unseen world is not distant or remote. It is intimately woven into the fabric of our existence. Billions of bacteria live on and inside your body right now, many of them crucial for your digestion and overall health. Microbes in the soil recycle nutrients, allowing plants to grow. Microscopic plankton in the oceans produce much of the oxygen we breathe. The wind carries countless spores, pollen grains, and tiny organisms across continents. It is a constant, silent ballet, a fundamental engine driving the processes of life on Earth. So, as you drift toward sleep, consider this magnificent secret. A world of incredible complexity and beauty, always present, always active. a hidden symphony playing just beyond the reach of your ordinary senses. We have only just begun to define its boundaries, to sketch the first maps of its vast territories. Tomorrow, perhaps, we can delve deeper into one of its most ancient and ubiquitous inhabitants, the fascinating world of bacteria, and uncover the roles they play in shaping our planet and our very lives. Imagine, if you will, the vast, silent canvas of space stretching out beyond our wildest dreams. It's not entirely empty, this cosmic ocean. No, it's sprinkled with something truly magical. Cosmic dust. These aren't just any specks. They are the ethereal remnants of stars, born from the fiery hearts of supernovae, those colossal stellar explosions that paint the cosmos with fleeting brilliant light. When a star reaches the end of its life, it exhales its essence into the void, a gentle sigh of creation that becomes the very dust we're talking about. Think of them as the universe's own celestial breadcrumbs, scattered across the infinite tablecloth of space, each one a tiny whisper of a story untold. What are these tiny particles made of? Well, they're surprisingly diverse. Many are silicates, much like the sand on our beaches, but forged in the extreme pressures of dying stars. Others are rich in carbon, the very backbone of life as we know it. And nestled within this cosmic glitter are often icy coatings, frozen water, ammonia, and methane, sometimes even complex organic molecules, the universe's own pre-packaged building blocks. These aren't just inert particles. They are tiny, intricate chemical factories drifting through the interstellar medium, carried by stellar winds and the gravitational currents of galaxies. They travel for eons, sometimes billions of years, a silent, unhurried journey across unimaginable distances, each speck a miniature time capsule, carrying the history of the cosmos, waiting for its moment to contribute. Eventually, some of these cosmic wanderers found their way to a young, tumultuous planet we now call Earth. Picture our world billions of years ago, a vibrant, restless place still cooling from its fiery birth. Volcanoes belched steam and gases into a nascent atmosphere, and vast, warm oceans swirled across its surface. It was a world of raw energy, a true cradle of creation, dynamic and ever-changing. The cosmic dust, along with larger meteorites and comets, rained down upon this early Earth, a constant, gentle shower of extraterrestrial gifts. Each micrometeorite, often no bigger than a grain of sand, carried its precious cargo of carbon and complex organic compounds, enriching the primordial oceans and land masses with the very ingredients needed for life. It was as if the universe itself was sending us a care package filled with the potential for something extraordinary, a silent promise delivered from the stars. Now, imagine these simple organic molecules, amino acids, the building blocks of proteins, nucleotides, the components of DNA and RNA, and fatty acids, which form cell membranes, swirling in Earth's warm, ancient waters. This wasn't just a random mix. It was a dynamic, reactive environment. Scientists like Stanley Miller and Harold Urey, in their famous experiment, showed how lightning striking a mixture of early Earth gases could spontaneously create amino acids. But there were other powerful forces at play. Deep beneath the oceans, around hydrothermal vents, superheated, mineral-rich water gushed from the Earth's crust, providing both energy and a diverse array of chemical catalysts. Clay minerals, with their intricate layered structures, acted like tiny molecular scaffolding, attracting and concentrating these organic molecules, encouraging them to link together, forming longer, more complex chains. It was a slow, patient dance, where simple ingredients, guided by energy and catalysts, began to weave themselves into more elaborate structures, like tiny builders assembling the first, most basic Lego bricks of life, piece by careful piece. The magic truly began when these increasingly complex molecules discovered the art of self-assembly. Think of it like a spontaneous embrace where certain molecules, particularly fatty acids, have a natural affinity for water on one side and repel it on the other. When enough of these fatty acids gather in water, they instinctively arrange themselves into spherical structures, tiny bubbles or vesicles with a double-layered wall called a lipid bilayer. These weren't yet living cells, but they were protocells, fragile microscopic envelopes that could encapsulate other molecules, protecting them from the harsh external environment and concentrating them within their watery interior. Inside these nascent bubbles, the conditions were just right for further chemical reactions to occur, shielded from the chaos outside. It was a crucial step, the formation of the first compartments, setting the stage for life to truly begin its journey, a quiet beginning for something profoundly significant. Within these protective protocells, another incredible development was unfolding: the emergence of self-replicating molecules. For a long time, scientists pondered whether proteins or nucleic acids came first. The RNA world hypothesis offers an elegant solution. RNA, or ribonucleic acid, is a remarkable molecule. Unlike DNA, which primarily stores genetic information, RNA can do both. It can carry genetic instructions, much like DNA, and it can also act as an enzyme, catalyzing chemical reactions, much like proteins. Imagine these early RNA molecules, perhaps formed on the surface of clay minerals and then encapsulated within a protocell, not only holding the blueprint for their own creation, but also actively helping to build copies of themselves. This dual capability was a game changer. It meant that a single type of molecule could kickstart the cycle of information storage and functional activity, leading to increasingly efficient replication and, eventually, rudimentary forms of metabolism within these tiny, self-contained worlds. These protocells, with their self-replicating RNA, were like the universe's first whispers of individuality, tiny laboratories of possibility, each one a potential ancestor to all life on Earth. Over countless millennia, these protocells, driven by the relentless forces of natural selection, began to refine their internal machinery. The RNA world eventually gave way to the more stable DNA as the primary genetic material, with proteins taking over most of the catalytic roles. The lipid membranes became more sophisticated, developing channels and pumps to control what entered and exited, allowing for more precise regulation of their internal environment. Metabolism grew more complex, harnessing energy from their surroundings to fuel their growth and replication. From these humble beginnings, from the cosmic dust that once drifted through the stars, through the spontaneous dance of molecules in Earth's primordial oceans, the first true living cells emerged. They were microscopic marvels, capable of self-replication, metabolism, and evolution, the very definition of life. Each one a tiny, self-sustaining universe, born from the grand tapestry of the cosmos, a testament to the incredible potential held within the smallest of things. And so, from the silent, ancient dust of distant stars, a remarkable journey unfolded, culminating in the first whispers of life on our planet. But the story of the microcosm doesn't end with the birth of the first cell. Oh no, that was just the beginning. For once life had taken root, it began to diversify, to explore, to evolve into an astonishing array of forms, each one a testament to the enduring power of these tiny, fundamental building blocks. Tomorrow, as you drift into dreams, we'll continue our journey, exploring how these single, simple cells began to work together, forming communities, and eventually creating the intricate, multicellular wonders that surround us today. For now, rest easy, knowing that even the smallest speck holds the potential for the grandest story. As we drift deeper into the silent symphony of the universe, let's turn our gaze inward, far beyond the stars, to the very fabric of existence itself. Imagine, if you will, the most fundamental building blocks, the tiny invisible architects that construct everything we see, feel, and touch. These are the atoms, the primordial dust from which galaxies, planets, and even you and I are spun. Each atom, despite its minuscule size, is a universe unto itself, a marvel of intricate design. At its very heart, nestled in a space so impossibly small yet incredibly dense, lies the nucleus. Think of it as the atom's tiny, powerful sun, or perhaps a precious pearl at the center of a vast, empty cathedral. Within this nucleus reside two kinds of particles: the protons, carrying a positive electrical charge like tiny sparks of pure energy, and the neutrons, their neutral companions, providing stability and mass like silent guardians. It's the number of these protons, this specific count, that defines an atom's identity. 1 proton makes it hydrogen, 6 makes it carbon, 8 makes it oxygen. It's like the alphabet of the cosmos, where each letter is unique and essential, dictating the very nature of the element. Sometimes, an atom might have the same number of protons, but a different number of neutrons. These are called isotopes, subtle variations that can give an element different properties, like the glowing tritium in a watch face. And swirling around this dense nucleus, not in neat planetary orbits as once imagined, but in a vibrant, probabilistic cloud, are the electrons. These are the atom's outer garment, its shimmering aura. Each electron carries a negative electrical charge, perfectly balancing the positive charge of the protons in a neutral atom. Imagine them as a swarm of incredibly fast, tiny fireflies, or perhaps a soft, fuzzy blanket of energy that envelops the nucleus. This electron cloud is where the atom truly interacts with the world, a bustling outer layer that dictates how it will behave, how it will connect. And here's a truly astonishing thought. Most of an atom is empty space. If the nucleus were a pea in the middle of a football stadium, the electrons would be like tiny dust motes flickering around the stadium's outermost seats, and everything in between would be vast, silent emptiness. Yet, it's this emptiness, this delicate balance of forces and particles, that gives matter its solidity, its presence, preventing us from simply passing through the chair we sit on. Now, picture these individual atomic letters, each with its unique character and its swirling electron cloud. They are not content to remain alone. They seek connection, a way to complete their outer electron shells, to find a state of quiet equilibrium and stability. And in this quest for balance, they reach out to one another, forming bonds like tiny, invisible handshakes or gentle embraces. This is where the magic of molecular complexity begins. One of the most common and elegant ways atoms connect is through what we call a covalent bond. Here, atoms don't give or take electrons. Instead, they share them, like two friends sharing a favorite book, or two dancers holding hands as they spin. They hold on to each other, creating a stable partnership. Think of two hydrogen atoms, each with one electron, coming together to share their electrons, forming a molecule of hydrogen gas, H2. Or consider the very air you breathe. Oxygen atoms, each sharing electrons with another oxygen atom to form O2, the vital breath of life. And water, that most essential elixir, is a beautiful example of covalent bonding. One oxygen atom gently holding hands with two hydrogen atoms, forming the familiar H2O, a bent, V-shaped molecule that gives water its unique properties, from its ability to dissolve so many substances to its expansive freezing. Then there are ionic bonds, a different kind of connection, often more like a generous gift. In this dance, one atom, perhaps with an extra electron it's eager to shed, might completely transfer that electron to another atom that has a strong desire to gain one. When this happens, both atoms become electrically charged, one positively, one negatively. And it's this powerful electrostatic attraction, like tiny magnets drawing together, that holds them in a strong, enduring embrace. Common table salt, sodium chloride, NaCl, is a perfect example. A sodium atom gives an electron to a chlorine atom, and then they are forever drawn to each other, forming the precise crystalline structure we sprinkle on our food, dissolving readily in water to release its constituent ions. From these fundamental bonds, molecules are born. Simple molecules, like the water and oxygen we just discussed, are like single words in the cosmic language. But just as words combine to form sentences, and sentences to form stories, molecules can link together in astonishingly complex ways, creating vast, intricate structures that are the very essence of life. Imagine building with an infinite supply of Lego bricks, but these bricks can connect in countless configurations, twist, turn, and fold upon themselves, limited only by the laws of physics and chemistry. Consider proteins, for instance. They are not just random chains of atoms, they are long, winding sequences of smaller molecular units called amino acids. These chains then meticulously fold themselves into incredibly precise, three-dimensional shapes, like molecular origami or intricate sculptures. Each fold, each twist, is crucial because a protein's specific shape dictates its function. It's like a key designed to fit only one particular lock. Some proteins act as enzymes, speeding up chemical reactions. Others form the very structure of our hair and muscles. Still others transport oxygen in our blood or defend our bodies against invaders. Their complexity is breathtaking, a testament to nature's ingenious design, where form and function are inextricably linked. And then there is DNA, the magnificent double helix, the blueprint of life itself. Imagine a spiral staircase, but each step is made of two molecular bases that pair up perfectly. This elegant, twisted ladder carries all the genetic instructions for building and operating every living organism on Earth, from the smallest bacterium to the largest whale. It's a vast library of information encoded in the precise sequence of these molecular steps, a testament to the incredible power of molecular architecture to store and transmit information across generations, ensuring the continuity of life. What's truly remarkable is that all this incredible diversity and complexity, from the simplest gas to the most intricate protein, from a grain of sand to a towering redwood, arises from a mere 100 or so different types of atomic letters. It's like having a small alphabet, but being able to write every book ever conceived, every poem, every epic saga. And sometimes, molecules can even have handedness, a property called chirality. Just like your left hand is a mirror image of your right hand, but cannot be perfectly superimposed, some molecules exist in two forms that are mirror images of each other. Often, only one of these handed forms will be biologically active, a subtle nuance that can mean the difference between a beneficial medicine and an inert substance, or even a harmful one. It's a reminder of the exquisite precision at this microscopic scale, where even a mirror image can alter destiny. So, as these tiny architects continue their silent work, building and rebuilding the world around us, we can find a profound sense of wonder in their intricate dance. The universe, in its grandest scale, is a tapestry woven from these invisible threads, each atom a knot, each molecule a pattern, contributing to the magnificent whole. It's a reminder that even in the smallest corners of existence, there is an order, a beauty, and a complexity that humbles and inspires. And as we appreciate the foundational architecture of atoms and molecules, our journey next takes us to the very energy that animates these structures, the forces that bind and break them, shaping the dynamic world of chemical reactions. For now, let your mind rest on these tiny, tireless builders, and perhaps as you drift to sleep, you'll feel the gentle hum of their endless work all around you. And so, as we drift deeper into the quiet hum of the night, let us turn our gaze inward, not to the vastness of the cosmos, but to a universe equally profound, equally wondrous, that exists all around us, and indeed, within us. We speak now of the intricate world of cells and microorganisms, a realm so tiny it remains invisible to our naked eye, yet so fundamental, it forms the very fabric of all life. Imagine, if you will, that every living thing you have ever seen, from the tallest redwood tree to the smallest ladybug, from the blue whale to a single blade of grass, and even you yourself, is built from countless infinitesimally small building blocks. These are the cells. Each cell is like a miniature, self-contained world, a bustling city or a cozy cottage, depending on its complexity, working tirelessly, silently, to keep the grander organism alive and thriving. There are two main types of these incredible tiny worlds. First, let's consider the simpler, more ancient ones, often likened to a charming, efficient studio apartment. These are the prokaryotic cells. They are the pioneers of life, the first forms to grace our planet billions of years ago. Imagine a tiny, self-sufficient bubble with its genetic instructions, its DNA floating freely within its cytoplasm, the jelly-like substance that fills its interior. There are no separate rooms, no intricate internal compartments. Yet, within this simplicity lies incredible resilience and adaptability. Bacteria and archaea, two vast and diverse domains of life, are made of these prokaryotic cells. They are the silent architects of our world, shaping environments, cycling nutrients, and even living harmoniously within our own bodies, performing tasks essential for our well-being. Then, there are the more elaborate, more complex worlds, the eukaryotic cells. If prokaryotic cells are studio apartments, eukaryotic cells are grand, bustling mansions, or perhaps even miniature cities, complete with specialized districts and departments. These are the cells that make up plants, animals, fungi, and a diverse group called protists. What makes them so different? Their defining feature is the presence of organelles, tiny membrane-bound structures, each with its own specific job, like different rooms or buildings within our miniature city. At the very heart of this eukaryotic city lies the bionucleus. Picture it as the city hall, or perhaps a vast ancient library, carefully guarded and central to everything. Within its protective membrane, it houses the cell's precious DNA, the complete blueprint, the instruction manual for the entire organism. It dictates what the cell does, when it grows, and how it reproduces. It's the wise elder, holding all the ancestral knowledge and guiding the city's every function. Surrounding the nucleus, within the flowing cytoplasm, that inner ocean, that living jelly that fills the cell, are other vital structures. Imagine tiny humming power plants scattered throughout the city. These are the mitochondria. They are the tireless engines, the energy factories, taking in nutrients and converting them into the fuel the cell needs to perform all its tasks. They are the reason you can move, think, and even dream, constantly generating the energy that powers every single process in your body. Then there are the intricate transportation networks and packaging centers. The endoplasmic reticulum, a vast maze of interconnected membranes, acts like the cell's internal highway system, transporting materials and helping to build proteins and lipids. Close by, the Golgi apparatus functions like the cell's post office or packaging plant, modifying, sorting, and packaging proteins and lipids into vesicles, tiny transport bubbles, ready to be delivered to their specific destinations, either within the cell or to be sent outside. And let's not forget the tiny, busy construction workers, the ribosomes. These are the protein factories found both freely in the cytoplasm and attached to the endoplasmic reticulum. They read the instructions from the DNA carried by messenger molecules and assemble amino acids into the complex proteins that do most of the work in the cell, from building structures to catalyzing reactions. Now let's expand our view beyond individual cells to the vast, unseen populations of microorganisms. These are the tiny living beings, often single-celled, that populate every corner of our planet. We've already spoken of bacteria and archaea, the prokaryotic wonders, but the microbial world also includes microscopic fungi, like yeasts, which help us bake bread and brew beverages, and the often overlooked protists. Protists are a wonderfully diverse group, a catch-all for any eukaryote that isn't an animal, plant, or fungus. They are the tiny hunters of the water world, the microscopic photosynthesizers that produce much of the oxygen we breathe, and the diverse dancers of the microbial realm, each with its own unique way of life. And then there are the enigmatic viruses. These are not technically considered living cells, as they cannot reproduce or carry out metabolic processes on their own. Instead, they are tiny packets of genetic material, DNA or RNA, encased in a protein shell. They are like microscopic messages, or perhaps intricate puzzles, that can only come to life by hijacking the machinery of other cells. They are a testament to the incredible diversity and sometimes surprising boundaries of what we define as life. Together, these cells and microorganisms form an invisible, interconnected web of life that underpins almost every process on Earth. They are in the soil, helping plants grow; in the oceans, forming the base of the food chain; in the air, drifting on currents; and within every living creature, playing crucial roles in digestion, immunity, and overall health. They are the silent majority, performing essential tasks that allow the larger, visible world to flourish. As you rest now, imagine these countless tiny worlds, these miniature cities and bustling apartments, working in harmony, a symphony of unseen life. It is a world of constant motion, of intricate design, of profound importance, all unfolding beneath the threshold of our perception. And as we consider this hidden complexity, we begin to appreciate the boundless ingenuity of nature, preparing us to explore yet another marvel, the incredible journey of life itself, from these tiny beginnings to the vast diversity we see around us. Imagine, if you will, that within each of your cells, within every leaf on a tree, within every tiny bacterium, there exists a universe of ceaseless activity. Not a silent, still universe, but one humming with purpose, a miniature city where countless tiny tasks are performed every second. This incredible dynamic hum of life, this constant state of doing and undoing, building and breaking, is what we gently call metabolism. Metabolism is the grand symphony of chemical reactions that keeps every living thing alive. It's the very essence of what it means to be alive, the continuous transformation of matter and energy. Think of it as the ultimate balancing act, a delicate dance between two fundamental movements, one that breaks things down and one that builds things up. Let's first drift into the world of catabolism. Imagine your cell as a busy kitchen, and you've just brought in a wonderful array of ingredients. Perhaps a complex carbohydrate like a starchy potato, a rich fat, or a protein-packed bean. Catabolism is the process of gently taking these larger ingredients and breaking them down into smaller, simpler pieces. It's like carefully dismantling a magnificent Lego castle, brick by tiny brick, not to destroy it, but to reclaim its valuable components, and, most importantly, to release the energy stored within its bonds. This released energy isn't just let loose, it's captured and stored in a special tiny energy packet, a kind of universal currency for the cell, called ATP, adenosine triphosphate. Think of ATP as the cell's rechargeable battery, ready to power almost every activity, from thinking a thought to moving a muscle, from growing a hair to repairing a tiny cellular component. It's the spark that ignites life's countless tiny engines. Now, once we have these smaller pieces and our pockets are full of ATP energy, we can turn to the other side of the metabolic coin, anabolism. If catabolism was the deconstruction crew, Anabolism is the team of master builders. It's the process where the cell takes those simple reclaimed bricks and, using the energy from ATP, meticulously constructs new, more complex structures. It might be building a new protein to help carry oxygen, or assembling a fresh membrane to enclose a cellular compartment, or even storing excess energy as a larger, more complex molecule for later use. It's like taking those individual Lego bricks and building a brand new, magnificent creation. Perhaps a gleaming spaceship or a cozy cottage, all according to the cell's intricate blueprints, patiently and precisely. But how do these incredible transformations happen so smoothly, so quickly, and with such precision? This is where the unsung heroes of the microcosm, the enzymes, step onto our stage. Imagine enzymes as highly skilled artisans, each one a specialist in a particular task. Without them, most of these chemical reactions would happen far too slowly to sustain life, like trying to build a complex machine with bare hands and no tools. Enzymes act as biological catalysts. They gently guide and accelerate these reactions, making them happen millions of times faster, without being used up themselves. Each enzyme has a uniquely shaped active site, like a perfectly crafted lock. Only the right key, a specific molecule called a substrate, can fit into this lock. When the substrate gently nestles into the enzyme's active site, a subtle change often occurs, a soft, induced fit, like a glove molding perfectly to a hand. This embrace allows the enzyme to either break the substrate apart, in catabolism, or join it with another molecule, in anabolism, before gently releasing the newly formed product and being ready for its next task. It's a dance of exquisite precision, ensuring that only the correct reactions occur at the right time, preventing chaos and promoting harmony within the cell. Let's delve a little deeper into how our cells truly harness that energy. When you eat, say, a delicious apple, your body breaks down its sugars, primarily glucose. This glucose is then carefully escorted into the cell's energy factories, often the mitochondria, the powerhouses we've spoken of before. Here, through a series of elegant, interconnected pathways known collectively as cellular respiration, the glucose molecule is systematically disassembled. It begins with a gentle splitting, like dividing a sweet fruit, in a process called glycolysis. The fragments then enter a circular pathway, often called the Krebs cycle, where more energy-rich molecules are extracted. Finally, in a breathtaking finale, these energy carriers deliver their precious cargo to a complex chain of proteins, where a cascade of electrons, like tiny sparks, generates a tremendous amount of ATP. It's a marvel of engineering, converting the chemical energy stored in your food into the universal energy currency that powers every beat of your heart, every thought in your mind, every quiet breath you take. But metabolism isn't just about energy. It's also about the intricate molecular interactions that define life. Every protein, every sugar, every fat molecule in your body has a specific shape, a unique three-dimensional architecture. These shapes are not accidental. They are crucial for how molecules recognize and interact with each other. Think of it as a vast, silent conversation happening constantly within you, where molecules speak to each other through their shapes, charges, and subtle vibrations. A hormone molecule, for instance, might travel through your bloodstream, searching for a specific receptor protein on a cell's surface, much like a messenger seeking a particular mailbox. Only when its shape perfectly matches the receptor's binding site will it deliver its message, triggering a cascade of events inside the cell. This exquisite specificity, this perfect fit, ensures that the right signals are sent, the right materials are transported, and the right reactions are catalyzed, all in perfect harmony, a testament to nature's profound design. Consider the creation of a protein, one of the most fundamental building blocks and workers of the cell. The instructions for every protein are carefully encoded in your DNA, like a master blueprint stored safely in the cell's nucleus. When a protein is needed, a messenger molecule, RNA, makes a copy of that specific section of the blueprint. This messenger RNA then travels out to tiny cellular factories called ribosomes. Here, like skilled assembly lines, the ribosomes read the RNA's code, linking together individual amino acids, the protein's building blocks, in a precise sequence. Each amino acid is brought to the ribosome by another type of RNA, ensuring the correct one is added at each step. This entire process, from DNA to RNA to protein, is a breathtaking display of molecular teamwork and interaction, where every component plays its vital role in bringing a functional protein to life. All these dynamic processes, the breaking down, the building up, the energy flow, the precise molecular conversations, are not random. They are meticulously regulated to maintain a delicate balance, a steady internal state known as homeostasis. Your body constantly monitors its temperature, its blood sugar levels, its pH, and countless other variables, making tiny adjustments all the time. If your blood sugar rises after a meal, hormones like insulin gently guide cells to take up glucose. If your body temperature dips, metabolic reactions might subtly increase to generate more warmth. It's like a masterful conductor leading an orchestra, ensuring every instrument plays its part perfectly, keeping the entire symphony of life in exquisite tune without you ever having to consciously think about it. So, as you can see, within the quiet confines of your cells, a bustling, vibrant world of dynamic processes is unfolding. Metabolism and molecular interactions are not just abstract scientific terms. They are the very heartbeat of life, the ceaseless activity that allows you to breathe, to dream, to grow, to simply be. It's a testament to the incredible efficiency and elegance of nature, a silent, powerful engine running within every living thing, transforming the raw materials of the world into the intricate tapestry of life. And as these remarkable processes continue their tireless work, ensuring the delicate balance within you, we can gently turn our thoughts to another fascinating aspect of this microcosm: the intricate ways in which cells communicate with each other, sharing information and coordinating their efforts to form the magnificent structures we call tissues and organs. But that, my dear listener, is a journey we shall embark upon next, as you drift deeper into your peaceful slumber. And so, as our gentle journey through the wonders of the microcosm continues, we find ourselves drifting deeper, past the familiar landscapes of cells and molecules, into a realm where the very fabric of reality takes on a new, shimmering quality. This is the quantum realm, a hidden universe of astonishing power and delicate balance, where the rules we know in our everyday world softly dissolve, replaced by a dance of probabilities and unseen energies. Here, at the heart of all existence, tiny particles are not just building blocks, but active participants in an intricate, silent ballet, choreographed by forces so fundamental they sculpt reality itself. Imagine, if you will, shrinking down, past the visible, past the microscopic, until you are smaller than a single atom. You are now in a place of profound stillness, yet also of immense, vibrant activity. Within this space, four fundamental forces act as the invisible hands, the silent conductors shaping everything from the smallest proton to the grandest galaxy. They are the architects of stability, the whisperers of change, and the weavers of connection. Let us gently explore each one, like turning the pages of an ancient cosmic storybook. Our first encounter is with the strong nuclear force. Picture it as the ultimate cosmic glue, a fiercely protective embrace that holds the very core of matter together. Within the nucleus of every atom, protons and neutrons huddle together, forming a dense, tiny jewel. Now, you might remember that protons carry a positive electrical charge, and like charges repel each other with considerable strength. So, what prevents these positively charged protons from flying apart, shattering the nucleus into countless pieces? It is the strong nuclear force. It is the most powerful of all the fundamental forces, a colossal strength that binds the quarks together to form those protons and neutrons, and then, with an even greater, more encompassing grip, binds the protons and neutrons to each other within that minuscule atomic heart. Its power is almost unimaginable, but its reach is incredibly short, extending only across the tiny, tiny distances within the nucleus. Think of it as a mighty guardian, standing watch over the atomic core, ensuring its stability. Without this fierce, short-ranged embrace, no stable atoms could exist, no stars could burn, and the universe as we know it would simply be a diffuse cloud of unformed particles, never coalescing into the rich tapestry of matter we observe. It is the silent, steadfast promise that the universe will hold together at its most fundamental level. Next, we encounter a force of subtle transformation, the weak nuclear force. If the strong force is the steadfast guardian, the weak force is the gentle alchemist, the quiet whisperer of change. This force is responsible for processes like radioactive decay, a phenomenon where unstable atomic nuclei transform, releasing energy and sometimes changing one element into another. Its most famous role is in beta decay, where a neutron, under the influence of the weak force, can transform into a proton, an electron, and an anti-neutrino. This involves changing one type of quark into another, a true shape-shifting act at the quantum level. Like the strong force, its range is incredibly short, even shorter in fact, making it difficult to detect directly in most circumstances. It is significantly weaker than both the strong and electromagnetic forces, yet its importance cannot be overstated. The weak force plays a crucial role in the nuclear fusion reactions that power our sun and other stars, slowly transforming hydrogen into helium, and over cosmic timescales, forging the heavier elements that are essential for planets, and indeed, for life itself. It is the force that allows the universe to evolve, to transmute, to breathe and transform, creating the diversity of matter from the primordial simplicity. It's a testament to the idea that even subtle changes can have profound, far-reaching consequences across the cosmos. Then, we meet the electromagnetic force, the grand architect and communicator of the quantum realm. This is the force we are perhaps most familiar with in our daily lives, though often without realizing its quantum origins. It acts between all electrically charged particles, like the positively charged protons in the nucleus and the negatively charged electrons that dance around it. It is the electromagnetic force that holds electrons in their intricate orbits around the nucleus, forming stable atoms. Without it, electrons would simply drift away, and atoms would cease to exist. But its influence extends far beyond the atom itself. It is the electromagnetic force that dictates how atoms interact with each other, forming the countless molecules that make up everything around us, from the water we drink to the air we breathe, from the rocks beneath our feet to the intricate structures of our own bodies. All chemical reactions, all the vibrant colors we see, the warmth of the sun, the spark of electricity, the pull of a magnet, all are manifestations of this single, elegant force. It has an infinite range, though its strength diminishes with distance, much like the light from a distant star. While not as overwhelmingly powerful as the strong nuclear force within the nucleus, it is vastly stronger than gravity at the atomic scale, and its long reach makes it the dominant force in shaping the world of atoms and molecules. It's the invisible network that allows matter to talk, to bond, to create the incredible complexity and beauty of our physical world. Finally, we briefly acknowledge gravity. At the scale of planets, stars, and galaxies, gravity is the undisputed cosmic sculptor, the gentle giant that pulls worlds together, orchestrates the dance of celestial bodies, and shapes the very large-scale structure of the universe. It acts on anything with mass or energy, and like the electromagnetic force, it has an infinite range. However, as we shrink down into the quantum realm, into the tiny teacup of an atom, gravity's influence becomes almost imperceptibly weak. It is by far the weakest of the four fundamental forces. Imagine a vast ocean liner, immense and powerful, but in the tiny teacup of the quantum realm, its presence is barely a ripple, overshadowed by the fierce currents and tiny whirlpools of the other forces. While absolutely crucial for the cosmos on grand scales, its role in shaping the microcosm, in dictating the behavior of individual particles within an atom, is negligible compared to the powerful grip of the strong force, the subtle nudge of the weak force, or the intricate dance of the electromagnetic force. These four forces, each with its unique personality and power, work in concert, a silent symphony that orchestrates the universe at its most fundamental level. They are the invisible hands that shape everything, from the smallest proton to the grandest galaxy, dictating the stability of matter, the energy of stars, and the very possibility of life. They are the fundamental rules of existence in this hidden, wondrous realm, ensuring that our universe is not a chaotic mess, but a place of structure, order, and breathtaking complexity. As we gently drift away from these foundational forces, these cosmic choreographers, we carry with us the understanding that even the most complex phenomena are built upon these elegant, fundamental interactions. Our journey through the microcosm continues, and next, we'll explore how these interactions give rise to something truly magical, the very essence of life itself, as we gently turn our attention to the intricate dance of biological molecules. As we drift deeper into the wonders of the microcosm, we arrive at a profound truth, one that whispers of an intricate dance woven through all life, the interconnectedness of microbes, environment, and our very own health. It's a story of invisible threads, pulling and weaving, creating a tapestry so vast and complex that it holds the very fabric of existence together. Imagine, if you will, the soil beneath your feet not as inert dirt, but as a bustling, vibrant city, teeming with microscopic architects and engineers. These are the bacteria, fungi, archaea, and countless other tiny beings that bring the soil to life. They are the Earth's quiet recyclers, diligently breaking down fallen leaves, dead plants, and the remains of creatures great and small, transforming them back into the fundamental nutrients that new life needs to flourish. Without these unseen decomposers, our world would be buried under layers of unprocessed organic matter, and the cycle of life would grind to a halt. They are the tireless custodians of the planet's pantry, ensuring that life's essential building blocks, like nitrogen, phosphorus, and carbon, are constantly replenished and made available for the towering trees and the smallest wildflowers. Consider the vital role of nitrogen. The air we breathe is full of it, yet most living things can't use it directly from the atmosphere. But deep within the soil, and sometimes in special nodules on plant roots, live remarkable bacteria. These are the nitrogen fixers, tiny alchemists who capture atmospheric nitrogen and convert it into a form that plants can absorb, like turning invisible air into nourishing food. It's a silent, profound miracle happening every second, fueling the growth of our forests, our crops, and ultimately, sustaining all life on Earth. These microbial partnerships with plants are ancient and essential, a testament to collaboration on the smallest scale. Then let us gaze upon the vast, shimmering oceans, the cradle of life itself. Here, in the sunlit upper layers, microscopic marvels known as phytoplankton and cyanobacteria perform an ancient life-giving ballet. These single-celled organisms, too small to see individually, collectively form the base of the marine food web. More astonishingly, through the process of photosynthesis, they breathe life into our atmosphere, producing more than half of the oxygen we inhale with every gentle breath. Every other breath you take, dear listener, likely comes from these tiny ocean dwellers. They are the lungs of our planet, quietly exhaling the very air we need to survive, while simultaneously drawing down vast amounts of carbon dioxide, playing a critical role in regulating Earth's climate. Even the very breath of our planet, its climate and atmospheric composition, is subtly orchestrated by these unseen maestros. But this grand symphony of life doesn't just play out in the vastness of the world around us. It resonates deeply within each of us, within the very sanctuary of our own bodies. Picture your body not as a solitary vessel, but as a magnificent living planet, hosting its own unique and diverse ecosystems. From the surface of your skin to the depths of your gut, trillions of microbes, bacteria, fungi, viruses, and archaea call you home. They outnumber your own cells by a factor of 10 to 1, forming what we call your microbiome. Within the winding pathways of your digestive system, your gut microbiome is a bustling, vibrant community. These microbial companions are like diligent gardeners, tending to your inner landscape. They help you digest food that your own enzymes cannot break down, unlocking vital nutrients and energy from the food you eat. They produce essential vitamins like vitamin K and certain B vitamins, which your body needs to function. More profoundly, they are crucial teachers for your immune system, helping it distinguish between friend and foe, guiding its development from infancy. A diverse and balanced gut microbiome acts like a wise elder, instructing your immune cells, ensuring they are robust enough to fight off true threats, yet tolerant enough not to overreact to harmless substances. And here's a truly wondrous secret. The whispers from your gut can reach your brain. This gut-brain axis is a two-way street, a superhighway of communication where microbial messages can influence your mood, your sleep, even your thoughts and behavior. The tiny inhabitants of your gut produce neurochemicals like serotonin, a key regulator of mood, and communicate with your brain through nerves and hormones. It's a profound connection, suggesting that the health of your inner microbial garden can profoundly shape your mental and emotional well-being. So, how does the vast outdoor world connect to this inner garden of yours? The answer, again, lies with our microbial friends. We are constantly exchanging microbes with our environment. Every breath, every touch, every meal brings us into contact with the microbial world. Think of the old friends hypothesis, a gentle idea that suggests early exposure to a diverse array of microbes from our natural environment, from soil, from animals, from other people, from simply playing outdoors, helps to train our immune systems to be robust yet tolerant. These old friends teach our immune systems not to overreact to harmless things like pollen or certain foods, potentially reducing the risk of allergies and autoimmune conditions. Our modern world, with its pristine surfaces and sometimes overzealous sanitization, can inadvertently limit this crucial microbial education. A less diverse exposure in early life might leave our immune systems less experienced, more prone to misidentifying harmless substances as threats. The food we eat also plays a pivotal role. A diet rich in diverse plant fibers, for instance, nourishes a wider variety of beneficial gut microbes, like a varied diet for your inner garden. Conversely, a diet lacking in fiber or high in processed foods can lead to a less diverse, less resilient microbial community, potentially impacting both digestive and overall health. Even the air we breathe, the water we drink, the very spaces we inhabit, carry their own microbial passengers, shaping the communities within us. Pollution, climate change, and habitat destruction in the wider world can ripple down to affect microbial diversity, both globally and within our own bodies. When this delicate balance is disturbed, either by environmental shifts or internal factors, it can ripple through our health, affecting everything from digestion to our resilience against illness. Understanding this intricate web, this cosmic dance between the smallest lives and the grandest systems, invites us to a deeper appreciation of our place within it. We are not separate from the world, but rather a living, breathing part of its magnificent microbial tapestry. Our health is inextricably linked to the health of the planet, and the unseen architects of life are the silent connectors in this grand design. As we gently close our eyes tonight, let us carry this awareness that every breath, every meal, every interaction is a connection to this vast living network. And as the stars begin to twinkle outside your window, we'll journey next into another fascinating aspect of these unseen worlds, exploring the incredible ways microbes adapt and evolve, a story of resilience and constant change. As we drift deeper into the wonders of the microcosm, imagine for a moment that you possess a secret key, one that unlocks doors to worlds unseen, worlds that dance and breathe just beyond the reach of your naked eye. For centuries, humanity has yearned for such a key, driven by an insatiable curiosity to peer into the very fabric of life, to understand the tiny architects and bustling inhabitants of the invisible realm. And so we began to craft our own keys, our own magnificent tools of discovery, each one a testament to our enduring wonder. Our journey into this unseen universe began with simple yet revolutionary acts of bending light. Imagine holding a tiny, curved piece of glass, much like a dewdrop magnifying a blade of grass. This was the humble beginning, the first whisper of what was possible. In the late 16th and early 17th centuries, ingenious minds, like the Dutch spectacle maker Zacharias Janssen, began to combine these simple lenses, stacking them one upon another. He created what we now call the compound microscope, a device that, for the first time, took a tiny object and made it appear significantly larger, revealing details previously hidden. It was like going from a blurry, distant glimpse to a slightly clearer, though still hazy, view. But it was another Dutchman, a draper named Antony van Leeuwenhoek, who truly became the first master cartographer of the microcosm. With incredible patience and skill, he ground his own tiny, perfect single lenses, achieving magnifications far beyond his contemporaries. He didn't just look, he saw. And what he saw through his simple, powerful instruments astounded him, and later, the world. He described animalcules, tiny, swimming creatures in a drop of pond water, the first glimpse of bacteria and protozoa. He saw blood cells, muscle fibers, and the intricate dance of spermatozoa. His microscopes were like personal, powerful telescopes pointed inward, revealing a universe teeming with life in every drop, every fiber. He was a pioneer, illuminating a world no one knew existed, a world that had always been there, quietly bustling, waiting to be discovered. Around the same time in England, the brilliant scientist Robert Hooke was also pushing the boundaries of observation. Using his own compound microscope, beautifully illustrated in his seminal work, Micrographia, he turned his gaze upon a thin slice of cork. What he saw were tiny, box-like compartments resembling the small rooms of a monastery. He named these compartments cells, a term that would forever become synonymous with the fundamental units of life. Hooke's observations, though limited by the technology of his time, laid the groundwork for the understanding that all living things are composed of these fundamental building blocks. These early instruments, the ancestors of our modern microscopes, relied on the magic of visible light. They are what we now broadly call light microscopes, or optical microscopes. Think of them as sophisticated magnifying glasses, using a series of lenses, an objective lens, close to the specimen, and an eyepiece lens for your eye, to gather and focus light that has passed through or reflected off a sample. The light carries the image, and the lenses bend that light to magnify it, much like a gentle river current guiding a leaf downstream. Over the centuries, light microscopy evolved, learning new tricks to reveal more secrets. The most common type, the bright field microscope, simply illuminates the sample from below, making it appear dark against a bright background. It's like looking at a silhouette against a sunny sky. But what if the subject itself is nearly transparent, almost invisible? Scientists developed ingenious solutions. Imagine trying to spot a ghost in a brightly lit room. It's hard. But what if you shone a light around the ghost, from the sides, so that only the light scattered by the ghost itself reached your eyes? This is the principle behind dark field microscopy. The specimen appears brightly lit against a dark, velvety background, making even the most translucent creatures shimmer into view, like tiny stars against the night sky. Then came phase contrast microscopy, a truly clever invention. Many living cells are mostly water, and they don't absorb much light, making them almost invisible in a bright field microscope. Phase contrast doesn't rely on light absorption. Instead, it plays with the phase of light waves. Think of light as ripples on a pond. When light passes through different parts of a cell, say the nucleus versus the cytoplasm, it slows down or speeds up ever so slightly, shifting its phase. Phase contrast microscopes cleverly convert these subtle phase shifts into differences in brightness, making the internal structures of living, unstained cells visible, like watching the invisible currents in a clear stream reveal themselves through the movement of tiny particles. It's like giving the invisible parts of a cell a gentle spotlight, allowing us to see their dance without disturbing them. And then there's the vibrant world of fluorescence microscopy. This technique is like painting with light. Scientists can attach special glowing molecules called fluorophores to specific parts of a cell or molecule they want to study. When illuminated with a specific wavelength of light, often blue or ultraviolet, these fluorophores absorb that energy and then re-emit it at a longer visible wavelength, usually green, red, or yellow. It's like shining a black light on a hidden message that then glows in brilliant colors. This allows researchers to pinpoint and visualize specific proteins, organelles, or even DNA sequences within a complex cellular landscape, illuminating the intricate pathways and structures with breathtaking clarity and color. Imagine a bustling city at night, where only the specific buildings you're interested in glow brightly, guiding your eye through the dark. However, even with all these clever tricks, visible light has a fundamental limitation, a natural barrier known as the diffraction limit. Think of it like trying to draw two very close lines with a thick crayon. Eventually, they just blur into one. Because light travels in waves, there's a physical limit to how small an object can be and still be resolved as two separate points rather than a single blur. For visible light, this limit is roughly 200 nanometers, about 200 billionths of a meter. This means that anything smaller than that, or any two features closer than that, remains a blurry mystery, a veil that light alone could not fully lift. To truly peer beyond this veil, to delve into the ultra-fine architecture of cells and even molecules, scientists had to abandon light altogether. They needed a new kind of light, one with a much shorter wavelength, capable of resolving incredibly tiny details. And so, in the 1930s, the electron microscope was born. Instead of using photons of light, these magnificent machines use beams of electrons. Imagine electrons as tiny, incredibly fine needles, much sharper than any light wave, capable of tracing outlines with exquisite precision. There are two main types of electron microscopes, each offering a unique perspective. The transmission electron microscope, or TM, is like an X-ray for the ultra-small. It fires a beam of electrons through an extremely thin slice of a specimen. As the electrons pass through, some are scattered, and others pass straight through, creating a shadow-like image on a detector. TEMs reveal the intricate internal structures of cells and organelles with astonishing detail. The delicate membranes of mitochondria, the stacked sacs of the Golgi apparatus, the tiny ribosomes dotting the endoplasmic reticulum. It's like slicing open a miniature world and seeing its entire internal plumbing and intricate machinery laid bare in stunning high-resolution black and white. Then there's the scanning electron microscope, or SM. Instead of passing through, the electron beam in an SEM scans across the surface of a specimen, much like a tiny paintbrush moving across a canvas. As the electrons hit the surface, they knock off secondary electrons, which are then detected to build up a detailed, three-dimensional image of the sample's surface topography. SEMs show us the textures, the bumps, the ridges, and the overall landscape of microscopic worlds. Imagine seeing the intricate scales on a butterfly's wing, the hairy legs of a dust mite, or the crystalline structure of a snowflake, all in breathtaking, almost sculptural detail. While SEMs don't reveal internal structures like TEMs, their ability to create stunning 3D-like surface images makes them invaluable for understanding the outer form and texture of the microcosm's inhabitants. But our quest for clarity didn't stop there. Even within the realm of light microscopy, scientists found ways to push the boundaries further. Confocal microscopy, for instance, combines the principles of fluorescence with a clever trick of optics. Using lasers to illuminate only a very thin plane within a specimen, and then employing pinholes to block out any light coming from above or below that plane, confocal microscopes create incredibly sharp, optically sectioned images. By taking many such optical slices at different depths, a computer can then reconstruct a stunning three-dimensional view of the entire cell or tissue. It's like taking countless perfectly focused photographs of individual layers of a multi-layered cake and then digitally stacking them to reveal the whole delicious structure in exquisite detail, free from the blur of out-of-focus light. And for truly feeling the contours of the atomic world, there's the atomic force microscope, or AFM. This remarkable tool doesn't use light or electrons at all. Instead, it employs an incredibly tiny, sharp probe, like a microscopic finger, attached to a flexible cantilever. This probe gently taps or drags across the surface of a sample. As the probe encounters bumps and valleys on the surface, the cantilever bends ever so slightly. A laser beam reflected off the cantilever detects these tiny deflections, allowing a computer to map the surface topography with atomic-level precision. Imagine a blind person reading Braille, but on a scale so small that they can feel individual atoms. AFM can even work in liquid environments, allowing scientists to study living cells and biological processes in their natural state, observing the subtle dance of molecules on a cell's surface. From the simple glass lens that first hinted at animalcules, to the sophisticated electron beams and atomic probes that reveal molecular landscapes, our tools of microscopic discovery have transformed our understanding of life itself. Each new invention has been a step further into the unknown, a new pair of eyes to witness the hidden beauty and complexity that underpins our world. These tools are not just instruments. They are extensions of our boundless curiosity, allowing us to venture into realms that were once pure imagination, revealing the intricate ballet of life at its most fundamental level. As we gently close this chapter on the incredible instruments that have unveiled the invisible, let us carry with us the sense of wonder they inspire. For with these powerful eyes, we have begun to truly appreciate the exquisite design and tireless activity within every living thing, from the smallest bacterium to the largest whale. And now, with these incredible tools in mind, we are ready to turn our gaze to the very first discoveries made possible by these inventions, to the foundational ideas that forever changed our perception of life itself. The profound insights of cell theory. Tonight, as we drift deeper into the quiet wonder of the microcosm, let us consider how these smallest of beings, often unseen, have woven themselves into the very fabric of our lives, shaping our health, our industries, and even the breath of our planet. They are the silent architects, the miniature alchemists, constantly at work, often without our conscious knowledge. In the realm of medicine, the microcosm's influence is nothing short of revolutionary. Think of a time, not so long ago, when a simple scratch could turn deadly, when infections swept through communities like an unstoppable tide. Then, a quiet moment of observation changed everything. Sir Alexander Fleming, in 1928, noticed a peculiar mold growing on a petri dish, preventing bacteria from thriving nearby. This serendipitous discovery gave us penicillin, the world's first true antibiotic. Imagine that tiny mold, Penicillium chrysogenum, producing a compound that could halt the growth of harmful bacteria, saving countless lives. Antibiotics, derived from these microbial wonders, work by targeting specific vulnerabilities in bacterial cells, perhaps disrupting their ability to build a cell wall or interfering with their protein synthesis. They are our microscopic shields, protecting us from invaders. Yet, even these powerful allies demand our respect, for the very bacteria they fight are themselves evolving, learning to resist, reminding us of the dynamic dance of life at this scale. Beyond fighting illness, microbes also teach our bodies to defend themselves. The concept of vaccination, for instance, is a profound testament to the power of the microcosm. By introducing a weakened or inactive form of a pathogen, or even just a piece of it, we gently nudge our immune system, like a patient teacher, to recognize and remember the enemy. When the real threat arrives, our body is prepared, armed with antibodies and memory cells, ready to mount a swift and effective defense. Diseases that once terrorized humanity, smallpox, polio, measles, have been tamed or even eradicated thanks to this ingenious microbial tutoring. It's a beautiful partnership. Tiny microbes presenting a lesson, and our bodies learning to protect themselves. And what about the bustling cities of microbes within us? Our own bodies are not solitary islands, but rather vibrant ecosystems. Trillions of bacteria, fungi, and viruses reside within our gut, on our skin, and in every moist crevice. This intricate community, particularly our gut microbiome, is a silent partner in our health. These good bacteria, like diligent gardeners, help us digest our food, breaking down complex carbohydrates that our own enzymes cannot touch, releasing vital nutrients. They also play a crucial role in shaping our immune system, teaching it to distinguish friend from foe. Some even produce vitamins, like vitamin K and certain B vitamins. When this delicate balance is disrupted, a state known as dysbiosis, it can ripple through our entire system, affecting everything from digestion to mood. It's a reminder that we are not just individuals, but hosts to a universe of microscopic life, and their well-being is intertwined with our own. Even in the cutting edge of modern medicine, microbes are at the forefront. Imagine tiny viruses, once feared, now repurposed as delivery vehicles in gene therapy, carrying corrective genetic material to ailing cells. Or consider CRISPR, a revolutionary gene editing tool whose origins lie in the ancient bacterial defense mechanism against viral invaders. These microscopic systems, honed over billions of years, are now offering us unprecedented ways to understand and mend the very blueprint of life. Moving from the delicate dance of health to the robust world of industry, the microcosm reveals itself as an indispensable workforce, powering countless processes we often take for granted. Think of the simple pleasure of a warm loaf of bread, its crust golden, its interior soft and airy. This transformation is a miracle of microbiology. Tiny yeast cells, Saccharomyces cerevisiae, consume sugars in the dough, producing carbon dioxide gas that makes the bread rise and alcohol that evaporates during baking. It's a miniature factory, turning simple ingredients into a culinary delight. This same principle of fermentation, orchestrated by various microbes, gives us an astonishing array of foods and beverages. The tangy creaminess of yogurt, the complex flavors of cheese, the crispness of pickles, the savory depth of soy sauce, the comforting warmth of beer, the elegant complexity of wine, all are gifts from bacterial and fungal collaborators. Specific strains of lactobacillus and bifidobacterium transform milk into yogurt, while different molds and bacteria ripen cheeses, developing their unique aromas and textures. These microbes are not just workers. They are master chefs, crafting flavors and preserving foods in ways we could never achieve alone. Beyond our plates, microbial enzymes are the unsung heroes of many industrial processes. Enzymes, proteins produced by living organisms, act as biological catalysts, speeding up chemical reactions. Microbes are prolific producers of these enzymes. Consider your laundry detergent. Many contain microbial enzymes like lipases to break down fats, proteases to tackle protein stains, and amylases for starches. They work tirelessly, breaking down grime at lower temperatures, making our cleaning more efficient and environmentally friendly. In textiles, enzymes are used to soften fabrics, stone-wash jeans, and even create natural dyes. In the pharmaceutical industry, microbes are engineered to produce complex molecules like insulin, vitamins, and even some vaccines, offering a sustainable and efficient alternative to traditional chemical synthesis. And looking to the future, microbes are at the forefront of sustainable solutions. Imagine microscopic algae, like tiny green solar panels, converting sunlight into energy-rich oils that can be refined into biofuels, offering a renewable alternative to fossil fuels. Or bacteria that can digest waste materials and produce biodegradable plastics, helping us tackle the global challenge of plastic pollution. Even in mining, microbes are being harnessed in a process called bioleaching, gently extracting valuable metals like copper and gold from low-grade ores, a more environmentally benign approach than traditional methods. The microcosm, in essence, is a vast, untapped resource of biological innovation, offering solutions to some of humanity's most pressing challenges. Finally, let us turn our gaze to the grandest stage of all, the environment. Here, the microcosm is not merely an influence, but the very bedrock upon which life on Earth thrives. These invisible beings are the planet's silent choreographers, orchestrating cycles essential for all macroscopic life. Consider the air we breathe and the soil that nourishes our food. The nitrogen cycle, for instance, is almost entirely driven by microbes. Nitrogen gas, which makes up about 78% of our atmosphere, is unusable by most plants and animals in its gaseous form. It takes specialized bacteria like the rhizobium, living in the root nodules of legumes, to fix this atmospheric nitrogen, converting it into ammonia, a form plants can absorb. Other bacteria then transform this ammonia into nitrates, further enriching the soil. Without these tireless microbial workers, the continuous supply of nitrogen, vital for building proteins and DNA, would cease, and life as we know it would grind to a halt. They are the planet's essential fertilizer factories, working ceaselessly beneath our feet. Similarly, the carbon cycle, the very rhythm of life, is profoundly influenced by microbes. While plants and algae perform photosynthesis, capturing carbon dioxide from the atmosphere, it is bacteria and fungi that act as the planet's primary decomposers. When leaves fall, when animals die, these microscopic recyclers break down complex organic matter, returning carbon, nitrogen, and other nutrients back to the soil and atmosphere, making them available for new life. They are the cleanup crew, ensuring that nothing is truly wasted, constantly replenishing the Earth's nutrient reservoirs. And what about the very air we breathe? A significant portion of the oxygen in our atmosphere, perhaps as much as half, is produced not by towering forests, but by microscopic phytoplankton, tiny algae and cyanobacteria drifting in the vast oceans. These minuscule organisms are the ocean's breath, performing photosynthesis on a global scale, converting sunlight into energy and releasing oxygen as a byproduct. They are the invisible lungs of our planet, sustaining us with every inhale. Even in the face of environmental damage, the microcosm offers hope. Bioremediation, the use of microbes to clean up pollution, is a powerful example. After an oil spill, for instance, naturally occurring oil-eating bacteria can be encouraged to multiply, breaking down the harmful hydrocarbons into less toxic substances. Certain bacteria can even neutralize heavy metals or degrade persistent pesticides. They are the Earth's tiny, tireless janitors working to restore balance to ecosystems disturbed by human activity. However, the influence of the microcosm on our environment is not always benign from our perspective. Some microbes, like methane-producing archaea in wetlands and the guts of ruminant animals, contribute to greenhouse gas emissions, playing a role in climate change. Understanding these complex interactions is crucial as we navigate the future of our planet. As we reflect on these profound influences in medicine, industry, and the environment, it becomes clear that the microcosm is not just a collection of tiny, isolated entities. It is an intricate, interconnected web of life, a hidden force that underpins our existence, constantly shaping our world in ways both subtle and dramatic. Their story is our story, intertwined and inseparable. And now, as the gentle currents of these thoughts carry us further, let us prepare to explore yet another facet of this hidden world, perhaps delving into the fascinating ways these tiny beings communicate and cooperate, forming communities that rival our own in complexity and purpose. And now, as we drift further into the quiet realms of the incredibly small, we find ourselves on the very edge of tomorrow, peering into a future frontier where the boundaries of what's possible begin to blur. Tonight, we'll explore two magnificent fields that promise to reshape our world, not with grand, sweeping gestures, but with the most delicate, precise touches imaginable: nanotechnology and synthetic biology. Imagine, if you will, tiny, invisible architects, no bigger than a whisper, working tirelessly to build and reshape the world around us, atom by atom, molecule by molecule. This is the heart of nanotechnology, the science of manipulating matter on an atomic and molecular scale, typically between 1 and 100 nanometers. To truly grasp how small this is, consider that a single human hair is about 80,000 to 100,000 nanometers wide. A red blood cell is around 7,000 nanometers. So, when we speak of nanotechnology, we are talking about a scale so minute. It's like trying to build intricate castles with grains of sand, except each grain is an individual atom, and our tools are as precise as a single thought. At this minuscule scale, materials often behave in astonishingly different ways. The rules of the macroscopic world, the world we see and touch every day, begin to give way to the strange and wonderful laws of quantum mechanics. A material that might be a poor conductor of electricity in its bulk form could become a superconductor when fashioned into a nanostructure. A substance that is opaque might become transparent. This shift in properties opens up a universe of possibilities. Think of the carbon atom, a humble building block of life. When arranged in a familiar lattice, it forms the soft, dark graphite in your pencil. But when those same carbon atoms are meticulously arranged into a hexagonal tube just a few nanometers in diameter, they become carbon nanotubes, materials stronger than steel, lighter than aluminum, and with incredible electrical conductivity. These tiny tubes are like nature's perfect scaffolding, promising to revolutionize everything from aerospace materials to super-fast electronics and even artificial muscles. In the realm of medicine, nanotechnology holds the promise of becoming our most delicate surgeon and most precise pharmacist. Imagine tiny nanoparticles, engineered to be biocompatible, acting like microscopic mail carriers. They could be designed to seek out specific diseased cells like cancer cells and deliver a potent drug directly to them, leaving healthy cells untouched. This targeted delivery could dramatically reduce the side effects of treatments, making healing a gentler, more efficient process. Researchers are also exploring nanobots, though still largely in the conceptual stage, that could one day patrol our bloodstream, repairing damaged tissues, clearing arterial blockages, or even fighting off infections from within. It's like having an internal maintenance crew working silently and diligently to keep our bodies in perfect harmony. Nanotechnology isn't just about building tiny machines, it's also about creating entirely new materials with unprecedented properties. Self-cleaning surfaces, where dirt and grime simply slide away, are already a reality thanks to nanoscale coatings. Imagine clothing that never stains, windows that never need washing, or paints that actively purify the air. We are learning to weave new fabrics of reality, thread by invisible thread, at the molecular level, giving us control over matter in ways that were once confined to the pages of science fiction. From these microscopic builders, our journey takes us to another realm of incredible precision, where we don't just build with the smallest components, but we begin to reprogram life itself. This is the enchanting world of synthetic biology. If nanotechnology is about building from the ground up, atom by atom, then synthetic biology is about reading life's instruction manual, the very DNA that makes us who we are. And then, with careful thought and gentle hands, beginning to write new chapters, new stories, or even entirely new books. Think of DNA as a biological computer code, a string of instructions that tells a cell how to grow, how to function, and what to become. Synthetic biologists are, in essence, biological programmers. They design and construct new biological parts, devices, and systems, or redesign existing natural biological systems for useful purposes. This isn't about creating life from scratch, but rather about understanding the fundamental components of living systems and then using that knowledge to engineer organisms with novel functions. One of the most profound applications is in medicine. For instance, bacteria and yeast have been engineered to act as tiny living factories, producing vital medicines like insulin for diabetics or artemisinin, a crucial anti-malarial drug, more efficiently and affordably than traditional methods. These microorganisms become our silent, microscopic pharmacists, brewing life-saving compounds in vast quantities. It's a gentle revolution in how we produce pharmaceuticals, moving towards more sustainable and accessible solutions. Beyond medicine, synthetic biology offers solutions to some of our planet's most pressing challenges. Imagine bacteria engineered to consume plastic waste, transforming it into harmless substances, or algae designed to produce biofuels more efficiently, offering a clean, renewable energy source. We could even engineer plants to capture carbon dioxide from the atmosphere more effectively, helping to mitigate climate change. These living solutions are like nature's own gentle cleanup crew, working tirelessly to restore balance. Researchers are also creating biosensors, living cells engineered to detect specific substances in their environment. A bacterium might be programmed to glow in the presence of a particular pollutant, acting as an early warning system for environmental contamination. Or a yeast cell could be designed to change color if a certain disease marker is present in a blood sample, offering rapid and non-invasive diagnostics. The tools of synthetic biology, such as the revolutionary CRISPR gene editing technology, allow scientists to precisely cut and paste sections of DNA, like editing a document with pinpoint accuracy. This means we can correct genetic errors that cause diseases or introduce new traits into organisms with unprecedented control. It's a profound responsibility, this ability to gently rewrite life's code, and one that is approached with immense care and ethical consideration. Both nanotechnology and synthetic biology invite us to imagine a future where we understand and interact with the fundamental building blocks of existence in ways we once only dreamed of. One builds from the ground up, manipulating atoms and molecules, while the other re-engineers life's own elegant designs, programming cells to perform new tasks. Together, they represent a quiet revolution, promising to bring forth solutions to challenges that once seemed insurmountable, all with the precision and grace of a whispered thought. As these visions of tomorrow gently settle in our minds, let us now turn our thoughts to another profound mystery, one that stretches not into the future, but into the vast, silent depths of the cosmos, where the grandest structures of the universe tell stories of beginnings and endings, of light and shadow. And now, my dear friend, as the day gently folds itself into the quiet embrace of night, let us take a moment to softly close the book on our wondrous journey. We have traversed vast, unseen landscapes, not with hurried steps, but with the gentle curiosity of a whispered thought. We have ventured into the very heart of existence, a realm so intricate, so profound, yet often hidden from our everyday gaze. Remember how we quietly stepped into that world, smaller than a speck of dust, yet teeming with life and purpose? We didn't need a grand telescope or a roaring rocket. Our journey was one of imagination, guided by the soft glow of understanding. We simply let our minds drift, like a feather on a gentle breeze, through the silent, bustling cities of the microcosm. We spoke of the tiny architects, the invisible builders that craft every leaf, every drop of dew, every beat of your own heart. We didn't name all their parts or chart every single pathway, for our purpose was not to memorize, but to marvel. We simply felt the quiet hum of their tireless work, the delicate precision with which they arranged themselves, forming patterns of breathtaking beauty and function. These are the ancient, patient hands that weave the very fabric of reality, a tapestry so fine, so detailed, it can only be truly appreciated with a quiet heart. And then we pause to observe the countless tiny dancers, the unseen inhabitants that flit and swim and glide through every corner of our world, and indeed within ourselves. We didn't need to understand their every move, only to feel the vibrant energy of their collective existence. They are the silent partners in life's grand ballet, each playing a vital, intricate role, contributing to the delicate balance that allows forests to grow tall and oceans to teem with life. Isn't it a comforting thought to know that even in the smallest drop of water, there is a universe of gentle activity, a symphony playing on, unheard by our ears, but felt by our souls? We didn't delve into complex theories or challenging equations. Instead, we simply allowed ourselves to be present with the idea that everything, absolutely everything, is made of these miniature wonders. From the solid ground beneath your feet to the soft air you breathe, from the light of the moon to the warmth of your own skin, it is all a magnificent assembly of the incredibly small. And in this realization, there is a profound sense of interconnectedness, a gentle reminder that we are all woven from the same miraculous threads, part of the same grand unfolding story. This journey wasn't about finding definitive answers, but about nurturing a sense of wonder. It was about feeling the quiet awe that comes from glimpsing the hidden artistry of the universe, knowing that beneath the surface of what we see and touch, there is an entire world of silent, intricate beauty perpetually at work. It's a beauty that doesn't demand attention, but simply is constant and true, a source of endless fascination and peaceful contemplation. As you lie here, nestled in the comfort of your bed, perhaps you can still feel the gentle echo of that tiny world within you. The same wondrous processes, the same delicate balances, the same tireless, invisible work is happening right now, keeping you safe, keeping you warm, keeping you alive. It's a reassuring thought, isn't it? To know that even when you are still, even when you are resting, the microcosm within you continues its gentle, life-sustaining dance. There's no need to grasp it all or to hold on to every detail. The true gift of our journey was simply to open our hearts to the possibility, to allow a quiet sense of marvel to settle within us, to understand that the greatest wonders are often the most subtle, the most unassuming, the ones that whisper their secrets rather than shout them. And now, as your eyelids grow heavy and your breath deepens, allow that feeling of gentle wonder to accompany you. The world, both vast and microscopic, continues its peaceful rhythm. The stars will twinkle, the moon will shine, and the countless tiny wonders will continue their silent, beautiful work, whether we are awake to observe them or not. Let your mind drift, knowing that the journey through the wonders of the microcosm doesn't truly end here. It simply transforms. As you close your eyes, perhaps your dreams will become new landscapes for exploration, new pathways into the unseen, where the tiny architects and the silent dancers will continue their ballet just for you. Sleep now, my dear friend, and may your dreams be filled with the quiet, comforting magic of the universe, both within and without. Good night.